My name is Carter Gotro. I will be doing a 6-minute talk on non-Newtonian fluids, the different types of them, and what they can be used for. So first, we need an introduction to viscosity. That would be a fluid's resistance to flow. If you want to put it in simpler terms, it's how sticky a fluid is, because honey is a lot stickier than water. It doesn't want to flow. If you ever try pouring honey, it sticks a lot because it has a much higher viscosity. Newtonian fluids, which are the opposite of what I'm going to talk about today, those are fluids that we're familiar with, like water. And the viscosity of those always remains the same, so every time you pour water, it pretty much pours the same way, because its viscosity doesn't really change. But I'm going to be talking about non-Newtonian fluids. Unlike Newtonian fluids, they do not have constant viscosity. The viscosity of a non-Newtonian fluid changes depending on the forces and shear stress that you enact on it. Like in this picture, the non-Newtonian fluid in the cup, whenever you pull the nail out of it, this viscosity freaks out and sticks to the nail. It acts like a solid, and then after the nail comes out, it goes back to acting like a liquid again. Some more examples of this are ketchup, cornstarch, and water, which is this mixture right here. Blood is a non-Newtonian fluid, and paint as well. So here we'll go into the 4 different types: shear thinning, thickening, and then thixotropic and rheopectic. So the first one is a shear thinning fluid. As the name suggests, the more shear rate you put on it, the thinner it gets, the more susceptible it will be to flow. An example of this is whenever you have ketchup in a bottle and it won't come out, you start slapping it and shaking it, putting forces on it, and it'll make it more susceptible to flow, and it'll flow out of the bottle. Another one is paint, because it's meant to stay in the container that you put it in, but whenever you want to paint it onto a painting, it needs to flow easily off the paintbrush. Other examples are blood, whipped cream, toothpaste, nail polish, and most lotions, for the same reasons of you want to keep them in a bottle, and then once you take them out the bottle, you want them to flow really easily. The second type is shear thickening fluid, or dilatant. It's the opposite of what I just explained. This is like that cornstarch and water mixture, where the more force you apply to it, the more it will solidify and resist flow. Like you see this person right here, if they put a lot of force on it and run on the mixture, it can support their weight. You just gotta move your feet really fast, because if you're not putting force on it anymore, you're gonna fall right through it. Another one is quicksand. Whenever you start struggling in quicksand, it like solidifies, but then if you sit still, it's gonna sink you. Real world applications are actually in body armors, because if you take a sudden blunt force with a shear thickening fluid, it'll solidify and protect you, which is pretty cool. So then we're going on to thixotropic fluids. This is basically a type of shear thinning, but the big difference between these and shear thinning is that it has a set amount of measurable time to where it can return to its normal state. It has a measurable time interval, like it says right there, which can range from a fraction of a second to hours. And then on the same note, rheopectic are basically shear thickening fluids that also rely on a time interval to re-thicken back up. A little easier way to visualize this is this table. Time dependent and time independent. You have your shear thinning and shear thickening, and then thixotropic and rheopectic with the application of shear. That's what happens to your viscosity. And then in a graphical way of looking at this, you have a Newtonian fluid compared to shear thinning and thickening based on shear strain and shear stress. And then this one shows that the viscosity of a Newtonian fluid stays the same, while shear thickening will rise or decrease based on the shear strain applied to it. In a mathematical term, you can see if a fluid is shear thinning or shear thickening based on the flow behavior index, which we characterize as the letter N. And if the N is less than 1, it's a shear thinning fluid, greater than 1, shear thickening, and equal to 1, it's Newtonian. And we calculate this using the power law equation, which is an equation consisting of shear stress, consistency index, shear rate, and power law index, like I said. The consistency index is a weird variable that determines the relative position on the stress axis, but yeah, it's defined by K. Then some real world applications of these things are some of the ones like I mentioned before, like food industry, ketchup, to flow easily whenever you pour them out of the bottle. Blood is actually a non-Newtonian fluid, and it's critical to understand how that works whenever you're trying to model something based on the circulatory system. Industrial lubricants use thixotropic greases so that whenever the machine is operating, it can be thin to allow the machine to move, and then it can thicken when it rests to reduce wear and tear. Like I said, body equipment can use shear thickening fluids to become rigid once they get a blunt force. And drilling and mining use drilling muds, which are shear thinning fluids to lubricate the drill bits and carry the debris to the surface, and letting the drill hole maintain stability. And so in conclusion, non-Newtonian fluids have a changing viscosity based on the shear stress. There's 4 types of these, like I said, that depend on how they react to shear and if that reaction is time dependent. These fluids are based on a flow behavior index, which is how you can mathematically calculate them. And all of these have real world applications ranging from the food industry to industrial machinery and even personal safety. These are the references that I used for all those pictures and research, and that's all I got. Any questions?